This is a picture of that first experiment, built of leftovers and stolen equipment. Over the next few years, it was improved by a team led by Alain Aspect in Paris, making its results more reliable. Over 10 years after Bell first proposed his equation, finally it could be put to the test. This is a modern version of the experiment first carried out by John Clauser and then Alain Aspect. Here, a crystal converts laser light into pairs of entangled light quanta, photons, making two very precise beams. These photons are passed round and bent back again until they pass through these detectors. We'll measure a property of the photons called polarization. And these dials here allow me to measure a second property of the photons as well. OK, so we're now going to switch on the laser and start the experiment. So this number here gives me the number of photon pairs coming through the experiment. The graph here dropping down gives me the probability that I can win, that I'm guessing right. The more photons, the more accurate it becomes. I'll stop at an uncertainty of about 1%. And the final answer is 0.56. So if I put that into my equation, I now need to run the experiment 3 more times, corresponding to the 4 different settings of these dials. And when I add them up and get the answer, if it's less than 2, then Einstein was right. If it's greater than 2, then Bohr was right. OK, so now for the second setting. OK, so the number I get this time is 0.82. Now reset for run 3. OK, so the run 3 result is minus 0.59. And finally, run 4. This last number will finally reveal if the world follows common sense or something much more bizarre. OK, so our final result is in, and it's 0.56. So if we turn the laser off... Right, I better just work out the answer. And there we have it, 2.53. It's a number greater than 2. Absolute proof that Albert Einstein was wrong and Niels Bohr was right. The significance of this result is simply enormous. Just remember what it means. Einstein's version of reality cannot be true. No amount of clever jiggery-pokery with our experiment can cheat nature. The 2 entangled photons' properties couldn't have been set from the beginning, but are summoned into existence only when we measure them. Something strange is linking them across space. Something we can't explain or even imagine other than by using mathematics. And weirder, photons do only become real when we observe them. In some strange sense, it really does suggest the moon doesn't exist when we're not looking. It truly defies common sense.
So this Bell's theorem and being able to test it is, in my opinion, one of the most significant, real intellectual leaps of last century. And the reason for that is because, as we showed, that there's no classical way that you can produce the correlations which we've observed in this experiment. And that means we need to abandon some of the classical notions of how we understand the world, whether it be reality, locality, and so depending on what your personal preferences are, then you scientists and physicists interpret this result in different ways. My own personal view is that you have to abandon one of 3 things. So whether the world is local, whether the world is real, or whether the world is causal. And my personal view, I don't have a preference. The scientific community is split over which one they often reside in. But for me, the foundations of quantum mechanics itself has a problem. So the very basic rules of quantum mechanics, when you write them down, two of them disagree. But we know quantum mechanics is the most beautiful theory that we've ever come up with. And so it's so open to such a variety of interpretations. And for me, I have a lot of sympathy with any interpretation of quantum mechanics that admits that there is a problem, or there is some conceptual misunderstanding, or we don't fully understand what violating Bell's inequality really means. And so my view is that I think it's a very important thing to think about, but I don't personally have an answer yet. But I think it's very fruitful to do these kinds of experiments so that we can be enlightened about what quantum mechanics is really trying to tell us about the world.
I also think that this type of experiment that we've built here and tested today, that manages to say something clear and simple about the interpretation of quantum mechanics, about the problems of interpretation in quantum mechanics, that is that local hidden variable models cannot be true, are of amazing importance because it's such a hard to define a problem. But as long as you realize how important locality is, I think the board-like attitude of not agreeing that something's real before you observe it is still a working attitude if you work in the lab. But you should know that you're in the presence of a great open problem, right? I don't think it's right to just ignore it. What I can say is that I care a lot about locality, so I think that not having instantaneous interactions in a model is very important. So I'm looking more towards models that just change hidden variables for something else, something maybe more complicated, something less trivial.